record. My SI session doesn't, or PEPCK phosphoenolpyruvate carboxylase. I have down pyruvate carboxylase. Let me check actually. Yeah, it is PEP carboxylase. My bad. PEP carboxykinase. Pepsica. Yeah, sorry, my SI session automatically records whenever I start it, so I don't think about this. Okay, so PFK is inhibited by ATP and activated by AMP. Likewise, fructose 1,6-bisphosphate is activated by ATP. And it doesn't really have an inhibitor that we talked about, except for citrate, which is in the liver only, right? Citrate is a D-citric acid cycle intermediate. It's actually where it gets the name, right? Citrate, the citric acid cycle. Okay. The other main points of regulation are that I have a whole document about the regulation of this. Oh, hexokinase is actually inhibited by G6P production, right? That's just to like, because if you're stalled here, right, you could get a backlog of G6P to F6P, that equilibrium there. You could get way too much of that. And so it just stops glucose from making more if you already have a lot of G6P. Okay, and then there is another inhibition with with pyruvate kinase, actually. Okay, pyruvate kinase, PK. This is the one that turns PEP into pyruvate, and it gives you an ATP. All right, so that's inhibited by ATP. Right, makes sense. You have a lot of energy. You don't want to be making more pyruvate. It is activated by fructose 1,6-bisphosphate, and then in the liver, it is inhibited by alanine, because alanine to pyruvate is like one step. Right, alanine looks like 1, 2, 3, and then you have a boop, boop, and then right, that's alanine, right? That to pyruvate is not particularly hard to get. Right, and so alanine in the liver inhibits pyruvate kinase. And then fructose 1,6-bisphosphate activates it, because if you have it going through here, right, movement out the bottom of this reaction, but like this step down here is the one that pushes all of these steps to happen. And so if nothing's flowing out here, right, you're just going to get this backlog of fructose 1,6-bisphosphate piled up, and you're going to have to rely on gluconeogenesis and waste all that energy you put in to store that energy again. So once it's here, we want to like get it out if we're trying to do glycolysis. Okay. That's it for glycolysis regulation, I'm fairly sure. Now, gluconeogenesis regulation, So gluconeogenesis regulation is just basically the opposite of glycolysis regulation. So fructose, F16 bisphosphate, or sorry, P. Yeah, right. So F16 bisphosphatase is activated by ATP, inhibited by citrate. PFK is actually activated by citrate, or no, inhibited by citrate in the liver. Yeah, and this is actually activated by it. Activated by high levels of energy. And then it is inhibited by AMP. And then ADP for the pyruvate to PEP. Both of these enzymes are inhibited by, so the PEP, CK, and pyruvate carboxylase, so PCA, right? Those are both inhibited by ADP here, right? So they're a little more sensitive to what the energy level is. And then PCA is activated by acetyl-CoA. In the liver. And yeah, I think that's it for glycolysis, that mess. Oh Lord, I'll have to condense that down. That'll be fun. But that's it for glycolysis. And gluconeogenesis, which is just backwards glycolysis. Let's talk about the pentose phosphate pathway. Okay, so pentose phosphate pathway, we start with a glucose, right? And that goes to G6P, which then gets taken off on this little shunt over here to form like this sort of intermediate, this glucose 1,6 delta lactone crap. Let me look up the actual name of it. Yeah, 6-phosphoroglucose delta lactone. I'm just going to do it D. Just do G delta lactone. Glucose delta lactone, or PG delta lactone. There we go. The PG delta lactone then gets fully oxidized. So in this step, we get an NADPH. And in this step, we take this and then we just sort of knock off a CO2. Yeah. 1, 2, 3, 4, 5, 6. Yeah, okay, this next step, we knock off CO2 to form, and we get out another NADPH to form RUP, I think. Ribulose, or yeah, ribulose 5-phosphate. Then that gets turned into either cellulose 5-phosphate or ribose 5-phosphate, which ribose 5-phosphate can then go to make nucleic acids. Okay, but these can also both combine, and through a series of steps, you end up getting one gap and one fructose 1,6 bisphosphate, I believe. No, fructose 6-phosphate. right? Which then you can turn the fructose 6-phosphate into fructose 1,6 bisphosphate, or you can go backwards, right? And so you get out 2 NADPHs for getting rid of 6 NADPH for 3 carbon dioxides created. Right? NADPHs are then used to go and make fatty acids, or to make fats, basically. Fats. Okay. We talked about how there are trans. So in this step here, right, there's a bunch of little swaps, right? You have trans ketolases, TKs, that move 2 carbons, and you have trans aldolases, which move 3 carbons. Right, so we use a combination of those two to end up getting a 6 and a 3. Yeah, 6 and a 3 carbon from, I think you get 2 gap actually. No, you get 2 of these. 2 for, 1 to 15. When you put in 8, you get 2 fructose 1,6 bisphosphate, or 2 fructose 6 phosphates and 1 gap per 3 glucose that come through. Right, so you take 3 here. You can get 3 of all these, and you go through and you get 2 fructose 6 phosphate and 1 glyceraldehyde phosphate, losing 3 carbon dioxides. All right. So if we talk about fructose metabolism, all right. So fructose metabolism. All right. So fructose in the muscle just goes to fructose 6-phosphate, which then goes through hexokinase, which then just goes into glycolysis. Fructose in the liver, however, gets turned into fructose 1-phosphate. That we don't like. And then so you can cleave that with fructose F1,6,1-phosphate aldolase. And you get 1 DHAP, which is nice, right? But then you also get a glyceraldehyde. Right, the DHAP can just go straight into glycolysis. No problem there, but the glyceraldehyde needs a little more work. So you could just use glyceraldehyde phosphatase, right? So glyceraldehyde phosphatase, right? Turn it into GAP, and then it can just go to glycolysis. Or you could also have glyceraldehyde be reduced by alcohol dehydrogenase. Or we could have glyceraldehyde be turned into, and the glyceraldehyde would be turned into glycerol, which can then go to foreign fats. Or that glycerol can then be phosphorylated, I believe. Or it could go through a couple more steps, become GAP, right? So you need like an ATP and you also need you also lose an NADH. Coming back, you gain an NADH, I believe, in this step. No, you lose an NADH in this step because you're reducing the glyceraldehyde glycerol, and you're gaining an NADH back at this step. So no energy change there. All right, the gap then goes to glycolysis, and we get, yay, fun, magic, right? But this glycerol step in the liver, this only happens in the liver. This glycerol step in the liver is not good for you because it helps promote fat creation, right? You don't want fats. You don't want your body to store fats, right? So that's why fructose is bad for you. Okay. Talked about fructose. We talked about glycolysis. Let's talk about fermentation. All right, so here's the fermentation. Right, so we have pyruvate. One method it can go through is just the citric acid cycle. Right, it can just go into the citric acid cycle, use it, and it's great. Have I been muted this whole time?
Nah, man.
Okay. How long is I muted for?
I came in at 7:45 and I heard everything you said since then.
Okay. Okay, Charlie just accidentally hit mute. Okay.
But can you tell me what that first thing you wrote under pyruvate says? It's hard for me to read it.
Ethanol, ETOH. It's just sort of like saying that this way is the ethanol fermentation, right? So we get acetaldehyde, right? We can then use alcohol dehydrogenase, which you lose an NADH there, right? Regenerate the NAD plus, but helps glycolysis keep going, and you get ethanol, right? These reactions, this reaction works both ways. This reaction is one way because we lose a CO2, right? And then lastly, the other way of fermentation is the lactic acid, or lactate, I should say. Lactate fermentation, you use lactate dehydrogenase. And then you form lactate, and you lose an NADH, right? So you get an NAD plus out of it. Okay, this can then, so this is a reversible reaction. This lactate can then go to the liver, where it will be turned back into pyruvate. All right, so we've got pyruvate that goes to lactate. Lactate then goes to the liver, then goes back to pyruvate, right? If we need a lot of energy in our muscles really quickly, right, we'll use our lactic acid fermentation. If not, then we'll use the citric acid cycle. Microbes tend to use ethanolic fermentation because it doesn't have that back reaction, right? And so you're not regenerating the useless pyruvate if you can't actually use it. So yeah, that's fermentation there. The CO2 there is why Alcoholic drinks are typically carbonated. And yeah, okay. So we did fermentation, we did pentose phosphate, we did fructose metabolism, we did gluconeogenesis. Okay, so let's talk about the intermediate of gluconeogenesis, oxaloacetate, right? Oxaloacetate, this enzyme here, pyruvate carboxylase. So pyruvate carboxylase, PC, only exists in the mitochondria. And we do gluconeogenesis in cytosol. And we have no oxaloacetate transporters. Right, so we have two ways of dealing with this. There is so we have to turn oxaloacetate into something, right? First way is the malate shunt, right? So you use alcohol dehydrogenase. To make it into malate. Okay, the malate then gets taken out, and you lose an NAD plus NADH to do it. Right, you use an NADH. Yeah, you lose an NADH to make the malate, and you take it out of the mitochondria. This is the mitochondria, and this is the cytosol. Right? You take it out, you turn it then back into oxaloacetate, and you get an NADH back. Right? This moves, the malate shuttle moves reducing power from inside the mitochondria to out. Right? So you don't move the NADH, you move the NAD plus, or you move the energy contained in the NADH from inside the cell to outside the cell, inside the mitochondria to outside into the cytosol. All right. The other shunt that we have is the aspartate shunt. Basically, there you take convert the oxaloacetate into aspartate, and then take it out of the cell, and then convert it back into oxaloacetate. All right, this one you don't really transfer anything. You transfer like a amino group, right? You transfer that from inside mitochondria to out, but otherwise you don't transfer anything. So when do we use the malate shuttle? Well, if we need NADH, when do we use the aspartate shuttle? If we don't need NADH, right? Because of NADH, if we use too much NADH, if we bring too much NADH out into the cell, right, glycolysis can't really occur, right? And so if we still need to be doing some glycolysis, we'll use the aspartate shuttle. If we don't need to be doing a lot of glycolysis, then we'll be using the malate shuttle. So yeah. Also, if we need if we need amino groups, right? So if we need this H2N stuff, then we can leave that out there, because this aspartate gets converted by taking an amino acid that doesn't have an amino group on it and adding that amino group to it. So this can be used for making proteins and other stuff like that. But I'm fairly sure that the thing he'll test you on is like, use the malate shuttle if you need NADH. Assuming he even asks a question about this, like when it would be more beneficial to have X or Y. Okay. Last thing we talk about is glycogen synthesis, right? So structure of glycogen. I'm not going to draw out the structure because that's a pain in the butt. What I'm going to do is I'm going to do horizontal lines. These are alpha 1, 4 linkages. And the vertical lines is an alpha 1, 6 linkage. Okay, if I put a line between them, right, this means there is 1, 2, 3, right? Or sorry, 1, 2, 3. Make that a little more simpler. 3 carbon or three sugars in this one, and then these horizontal ones are always 1 long. Okay, so glycolysis. Not glycolysis. Glycogen has the structure, right? You have these like side chains all coming off of this big branch, right? This big branch. What is the structure? Why is it useful? It increases solubility. If we just had a long one-stranded string of glucose, then it wouldn't be very soluble. Look at cellulose. Fiber is not very soluble in water, and it's for that reason, right? This lets us get more surface area, more areas for more ways for like this to integrate into the liquid, and so it increases solubility, and it's easier to get at, right? So we have these branches, right? You can do it on this branch. You can do chemistry on this branch, and this branch. So you get three sites instead of one site. You would have just a straight line, right? Straight line only has 1, whereas this branch structure has 3. Okay, or well, it has theoretically far more than 3, right? You could have a bunch of branches, but the one that I drew has 3. All right, so that's why we have the structure of glycogen. Okay, so let's talk about breaking down glycogen, right? Glycogen breakdown. All right, so when it comes to glycogen breakdown, we have 3 enzymes. Number 1 is going to be glycogen phosphorylase. Okay, glycogen phosphorylase takes a UTP plus a glucose, and then, this is glycogen breakdown, right? So it takes a UTP plus a glycogen, turns it into a smaller glycogen, and a G1P, right? This needs a vitamin B6 derivative to work. And the delta G not standard of this reaction is basically 0, but wait, no, this doesn't need am I doing the wrong one? Hang on. Oh no, UTP is the synthesis one. I forgot. Okay, so this takes actually a phosphate and a glycogen, right? Phosphate plus glycogen gives you a glycogen N-1 and a G1P, right? Delta G is about 0, but concentration of phosphate is really, really high, and so pushes it rightwards. You can basically, so when it comes to this enzyme, right, it has it can cut up to 4 to 5 glucose that are alpha 1 4 linkage left. Right, so it can cut the structure to 1, 2, 3, 4, 5, 6. Right, it can cut until it's 1, 2, 3, 4. Right, so it can cut up to here, but once it gets past here, right, it can't cut any further. And it also cannot cut this branch site, right? So it can't cut this branch site and can't cut anything further than here. All right, so next we have, after glycogen phosphorylase, you get glycogen debranching enzyme, right? Glycogen debranching enzyme. Right, glycogen debranching enzyme, what it does is it takes this sort of strand right here that can't be cut, and it moves it and puts it down here, right? And so we get a structure that's like this, right? So you just move it on to another part, right? And from there on, you can push, you can glycogen phosphorylase it from there. All right, but it leaves one single alpha 1,6 linkage here. Okay, and that is for our next one. But actually, no. So you actually take water. It actually also takes water and makes this one pop off as glucose, not as G1P. Right, so the rest of them are fed as G1P. This one is only fed as glucose. Okay, and then finally, we get a G1P as opposed to a G6P, right? The glycolysis use, we have to fix that. So we have phosphoglycerate mutase. Basically, its whole job is G1P to G6P. And how it does this, right? It does it the same way that the glycerate mutase, or phosphoglycerate mutase does it in glycolysis. So it has this histidine residue that is phosphorylated, right? And so you make it G1P, you turn that into G16 bisphosphate, and then you turn that back into G6P with getting off the protonated histidine back, right? So histidine, or sorry, not protonated histidine, the phosphorylated histidine, right? So you get the you lose the phosphate here, right? That gets put there, and then you gain the phosphate back in this step. Same mechanism as the one in glycolysis. All right. Regulation. Okay, well, we'll talk about regulation at the very end. So for synthesis, we have 3 enzymes again. Right, so our first enzyme is the one that I was thinking of originally, where we take first enzyme for synthesis is UDP glucose pyrophosphorylase. All right, so we take a G6P, right? So we take a G6P, or no, sorry, G1P. We take a G1P and we add a UTP to it. We get a UDP glucose hybrid with a pyrophosphate, which then goes to be 2-phosphate, ensuring that this reaction will keep going this way. It will only go this way because of this pyrophosphate, this pyrophosphorylase step right here, which turns the pyrophosphate to 2-phosphate. Okay, so we get this UDP glucose little mixture. And then we take the UDP glucose thing, glucose, we add it to a glycogen of N length, and it goes to glycogen N plus 1, right? So we just extend the chain. So originally we have a strand like this, right? We just add another little block to it. All right, finally, so how do we make the branches? Well, this is glycogen branching enzyme, right? So branching enzyme. And so if you have a strand of, I believe you need a strand of 7-glucose, right? And it can make an alpha 1,6 bond, creating a new branch, as long as that branch is 4 away from last one. Okay, so it takes a sort of glucose here, right? Let's say this is a 7-glucose chain right here, cuts it here, makes a, moves it to here, right? And then makes a alpha 1,6 bond with the terminal end of this one. And so we get a branch. This branch, right, precludes any branches that are not 4 glucose away from this one, right? So this one, and then 4 away from it in either direction, cannot form another branch. All right. Okay, that's fun. Now, let's talk about regulation. The thing Texas failed to wanted to avoid, and that's why we're in this mess in the first place. Okay, so when we are with glycogen, all right, so we start with glycogen. Okay, and then we can break it down using a phosphate in the debranching enzyme. With pyrophosphorylase, or sorry, then the debranching enzyme. We can break that down into G1P, and that can be turned into G6P. And then this G1P can also be turned into UDP glucose, which can then go up into this, which will have the branching enzyme and synthase rate. So the things that limit breakdown, right? Breakdown is inhibited by a MP. No, wait, breakdown is inhibited by high ATP levels and lots of G6P and glucose, but only in the liver. All right. It is activated by AMP, right? Just like basically everything to do with energy is. And then the synthesis is activated by ATP, right? You have a lot of energy. You want to store it, and is inhibited by ADP. All right, and that's what I have down. Last thing is the synthase in pyrophosphatase. Let me see, hang on. So the synthesis in phosphorylase, right? Right, they have a B and an A form, right? So they're the same enzyme, right? They just add or subtract a phosphate to it, right? So if you have a phosphate added to it, right, that is going to activate the breakdown. Okay, so whatever is going to push that arrow more towards the breakdown, it's going to do. All right, for the synthase and the phosphorylase. Okay, so the synthase, so phosphorylase A is active and synthase A is active, right? So the A is always active, the B is always inactive. Okay, the phosphate goes on whatever will make the breakdown favorable. All right, so for phosphorylase A, right? Phosphorylase is the one that breaks it down, right? So the A form, the active form, is the one that's going to be created when you phosphorylate it. Okay, for synthase, right? The A form is going to be the one that makes the glycogen. We don't want that. So the B form is the one that doesn't make the glycogen. And so we want to put a phosphate on that one. Or the phosphate will be the one, the phosphorylated enzyme will be the one that will be the B form for synthesis, right? So this is one for that, and that's the one for that. I don't know a better way to put it, but all right. Okay. And in the liver, right? In the liver, glucose is the main inhibitor for the phosphorylase. For breakdown, right? Glucose is the main inhibitor, right? Phosphorylation we only really deal with that in the muscles. In the liver, right, we care much more about how much glucose do we have. Do we need to make more? Do we need to keep storing it? What? So in the liver, we just care about glucose concentration. But in the muscle, we care about this phosphorylated A or B form. Right? A is always the active form. B is always the inactive form. And the phosphorylated one will be the form that has the phosphate on it will always be the one that pushes it towards breakdown of the glycogen. Okay. So all of that's there. Let's go ahead and work through a problem. In a general term, so he's almost certainly going to give us a question where it says you have a radio label C14 on carbon N of glucose, right? Where will it end up in pyruvate? All right. So if we think about glucose, right, we think about the how we name the carbons, CH2OH, right? This is carbon 1, 2, 3, 4, 5, and then 6. All right. So if we have carbon 1, 2, 3, 4, 5, 6. All right. So there are two pathways that this glucose, or that any one carbon on this glucose can go. It can go to GAP, or it can go to DHAP, which then both end up going to pyruvate. Right? So if carbon 1, right, and the way that this will end up working is carbon, so GAP looks like, glyceraldehyde phosphate looks like, here, I'm going to go ahead and just draw GAP. Glyceraldehyde phosphate looks like this. COH C with a phosphate, right? And then DH, dihydroxyacetone phosphate, looks like CCC with an OH, carbonyl, and then phosphate, with this being carbon 1, 2, and 3, and 1, 2, and 3. Okay, now from the notes, we know that he has given us, from the notes, we know that for the GAP, so the carbon on glucose that this one goes to for GAP is going to be carbon 6. This is 5. This is 4. And then this one down here is 1, 2, 3. Carbon 1, carbon 2, carbon 3. All right, makes sense, right? Because the phosphate is on the 1 and the 6. At the from fructose 1,6-bisphosphate, it's on the 1 and the 6 carbon, right? So the phosphate should be 6 and 1 respectively, right? And then just count down or count up depending on what makes sense. All right. DHAP is formed from the first 3, and GAP is formed from the second 3. All right. Now, from this, right, these will both keep their numberings for pyruvate, which looks like O, and then C double bond O, and then CH3. All right, so this is carbon 1, 2, and 3 of pyruvate. All right, and they will keep the same numbering, right? So if we start with carbon 1, we're ending up on position 3 of pyruvate. This is in the glucose, right? This is in pyruvate, right? Carbon 1 is going to end up in position 3. Carbon 2 is going to end up in position 2. Carbon 1 is going to end up in, or carbon 3 is going to end up in position 1. All right, carbon 4 is going to end up in position 1. Carbon 5 is going to end up in position 2. Carbon 6 is going to end up in position 3. All right, so that is our little key there. And so if we go backwards from this, right? So he can also ask us, now what carbon in glucose will the pyruvate end up in? Okay, and there, from this, we actually have 2 pathways, right?
Hey, sorry to interrupt you. Could you go back? I was copying down the key.
Copying down key, yeah.
Sorry, man. You're so good. You move so fast. All right, I'm good. Thank you.
You're all good. All right, I'm gonna leave it there for a couple more seconds, just to let everybody get there. I posted this in the chat as well at some point when I was working it out. Okay, but now we need to write our key for pyruvate to glucose. right? So if you're pyruvate, right, you get to be a different carbon depending on whether or not we get formed back into DHAP or GAP, right? Because remember, we need both GAP and DHAP to make glucose again in gluconeogenesis, right? And so we're going to have two different possible places in which it can form, and it can be found in the glucose made back from gluconeogenesis. All right, so if it's pyruvate 1, right, and we look at our P over here, it can be glucose carbons 3 or 4. If it is pyruvate carbon 2, it can be 2 or 5. If it is pyruvate 3, it can be 1 or 6. And that is how you do that problem. Not the hardest to remember, right? Just the middle two go to 1, out from that you go to 2, out from that you go to 3, and then you can work backwards to find if you have pyruvate at 1, 2, or 3, it's going to end up as 3 or 4 in glucose, 2 and 5 in glucose, and 1 and 6 in glucose, right? Makes sense that you'd have two positions in which it can be found because pyruvate has 3 carbons, whereas glucose has 6 carbons. Yeah. All right. Structure of ATP. That is another one. So it is phosphates are the easiest thing to draw. I always just put all of the double bonds on the phosphates facing up, and then all the single bonds facing down, right? Negative, 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 negative. Okay, you go down. It is a hexagon with an oxygen on the top, an OH going down here. Okay, and then you go up and you get into the real annoying part, which is the adenine or the adenine. All right, so adenine is a nitrogen, and then boom, boom. Okay, that is the first ring. If you think about it, right, if you spend a lot of time thinking about it, you realize that adenine is aromatic. And if you remember your aromatic from CHEM, it can kind of help you figure out where the double bond should or shouldn't go. But at this point, I just say memorize it. It's not like you're going to have to memorize and learn a bunch of nucleic acids. Okay, so this is NH2, and then down, down. Okay, this one, all right, so you have a 5-member ring and you have a 6-member ring. The 6-member ring just looks like benzene, right, with a nitrogen here and here. And then there's also an NH2 coming off the top there. And that is adenosine triphosphate, ATP. This is ribose, right there. That sugar right there is ribose. Just as a remember. What else do we think he's guaranteed to talk about? There weren't a whole lot of other ones that were like, I know he's going to ask a question about that. On practice test, there was one that was like draw fructose 1,6-bisphosphate, or sorry, 2,6-bisphosphate. That one should be pretty easy. If you remember glucose, right? Glucose is the OH is down, down, up, down, and then the CH2OH is also up. And then the fructose should follow that pattern as well. Just starting with carbon 1, carbon 2, carbon 3, carbon 4, and then carbon 5 has the CH2OH, and then carbon 6 is the CH2OH. So so like fructose, right, would be the same thing. Down, up, down, down, except this down one would be CH2OH. So fructose would look like this basically. Up, 2OH, down, wait, 1, 2, 3, 4. Either way there. So down, so 1, 2, 3 is up, down, and then down with CH2OH. Like that, right? And then you can put the phosphates wherever they should go, right? Phosphates just replace an alcohol. There was a question where he gave us like a table and was like, the table had like standard delta G's of certain stuff, and it was like, what would be like the standard energy of formation for like, or the standard delta G for like phosphorylating X group on this, right? And you have to figure it out. That shouldn't be too bad. For last exam 2B, it should be 1.6. Yes, it should be 1.6. His work says 1.6, but his answer says 1.3. So I think he just sort of goofed it. We could all spam him with emails. That might be fun, but also probably get him to hate us more than he does already. All right, there's not much more I can think of. It's just a lot of memorize your enzyme names and in the order and what they do. No lab this week. We're doing experiment 2 next week, so that'll be fun. And yeah. All right. Anyone else have anything to add? We might start doing it. We might start doing this for Dr. Shee's class, but I kind of hate his class. So, well, I don't hate it, but it's on Blackboard Collaborate, and Blackboard Collaborate is awful. So yeah, y'all stay warm, be safe, don't do